Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on exponential growth and decay. So we'll have an emphasis on compound interest, which is a type of exponential growth, but exponential growth and decay can happen in heaps of other areas. We'll also look at growth and decay in terms of population. So I'm actually going to explain the difference between compound and simple interest so we can get an understanding of what exponential growth actually means. So let's first have a revisit of simple interest. So look at this example here. I invest $20,000 at 10% per annum interest. So firstly, I will look at what happens if that is 10% per annum simple interest. And you did simple interest last year, and it is pretty simple. So we just find 10% of $20,000, okay? And hopefully you can do that without a calculator. So 10% of $20,000 is just $2,000. So what happens with simple interest is the amount that's in your account, the amount you have, would go up by $2,000 each year. It will go up by 10% of what you started with each year. So at the end of the first year, you would have $22,000. At the end of the second year, you would have $24,000, and so on. You see that each year the amount you have is going up by the exact same amount. So when it goes up by the same amount, it's going up, so it's still growing. Your investment is growing. We call this linear growth, going up by same amount each time. Okay, so that's what you did last year with simple interest. Let's look now at what it would be with compound interest. So I guess it's called compound because not only do you earn a percentage of principal in the interest, the principal being $20,000, what you start with, you don't earn just a percentage of that, you also earn a percentage of the interest you've already earned. So let's look at how compound interest would work. So 10% of 20,000 is 2,000. So after the first year, with compound interest, you'd still have the same amount, 22,000, right? But after the second year, I wouldn't find 10% of 20,000, I'd find 10% of 22,000. So 10% of 22,000 is 2,200. So at the end of the second year, I have to add on 2,200. Now to find out how much I would have after the end of the third year, I don't find 10% of what I started with, I find 10% of the previous year. So 10% of 24,200 is 2,420, so I need to add that on, 2,420. So you can see I now have more with compound interest than I would with simple interest. And then let's say we do it again for the fourth year. So again, I wouldn't find 10% of what I started with, I would find 10% of the previous year. So 10% of 26,620 is 2,662. So I had 2,662. And you can see there's quite a difference here. Now I have 29,282 instead of 28,000. So there's more than 1,000 difference. But what I want you to know is the amount that the investment is increasing by is going up each year. So for the first year, at the end of the first year, I started with 20,000. I went up by 2,000 in the first year. To go from the first to the second year, I went up 2,200. Then it increased by 2,420, and then it increased by 2,662. So hopefully what you can see is, unlike simple interest, which is linear growth, when I have exponential growth, which is what compound interest is, the amount it's going up by increases. So if you like, the investment is increasing at an increasing rate. The amount it goes up by each year is also increasing. And that is what exponential growth is. It's much faster growth. So increasing at an increasing rate is the idea behind exponential growth. So that luckily there is a formula you can use for exponential growth, and I'll show you that now. So for compound interest, we have its own formula, but it is one of the general formula for exponential growth anyway. So the amount you have is how much you started with. We call that P for principal. That's what we called it in simple interest last year as well. And what you do is you times it by 1 plus R, which is the interest rate, to the power of n. Okay, so the formula here is, if I'm getting compound interest, the amount I have after a certain time is the amount I started with. Now this 1 plus R business means increasing by R%. So if you want to increase by 10%, you times it by 1.1. If you want to increase the number by 25%, you times it by 1.25. And this n means you're doing it n times. You're doing it a number of times. So let's look at an example. So let's do this question here. It's actually the same situation that I had on the previous slide. So I invest $20,000 at 10% per annum, compounded annually, and I want to know how much money would be in the account after 10 years. So I don't want to do what I was doing on the previous slide and find out how much after year 1, after year 2, year 3, all the way up to year 10. That would take too long. So what I'm doing is I'm finding the amount. So the amount is how much I started with. So I times it by 1 plus, so this little r means you have to write the percent as a number. So 10%, you need to write it as 0.1. That's what 10% is as a decimal. And I raise it to the power of 10 because that's how many years I have the investment for. What this is doing is taking my amount, 20,000, then it is increasing it by 10%, and then increasing that number by 10%, then increasing that number by 10%. It's doing that 10 times. So if I just put that on my calculator, I see very quickly I have about 51,875. That's to the nearest dollar. Okay, much quicker way than finding year 1, year 2, year 3. Okay. So if it was simple interest, I would have gone up by $2,000 a year. So after 10 years, I would only have 20,000 plus 10 times 2,000, 40,000. So compound interest, when you invest it, it goes up rapidly, much more rapidly than simple interest. Okay, so we're now going to look at another application of exponential growth. So let's have a look at this question here. Now, it doesn't involve compound interest, but it's the same sort of idea. It's exponential growth. So the population of a town, 350,000, it increases by 2% each year, and we'll find the population in 20 years. So when we say increases by 2% each year, we don't mean that it increases by the same amount. So 2% of 350,000, what's that? That'd be 7,000. So we're not saying that it increases by that number each year. It increases by 2% of the population from the previous year. So if 350,000 was the population in 2018, increase it by 2%, that's the population in 2019, increase the population from 2019 by 2%, and that's the population in 2020, and so on. So the population is increasing by 2% of what it was the previous year. So it's going to increase at an increasing rate. Each year, the population is going to increase by a larger amount. So we can use a similar formula to that for compound interest. So this is the general formula for exponential growth. So A is what you're trying to find is A0 times by 1 plus R to the power of n. So here A0 has the same meaning as P did in interest principle. It's how much you start with. Again, R is the rate. It's 1 plus R. R has to be as a decimal, I should say. So it's 1 plus R because we're increasing by that amount. And N is just the number of times that the thing has been increased. So it's the number of increases. So in our example here, so the amount would be A0, which is how much I started with, times by 1 plus R. So I have to make R a decimal. So 2% is the same as 0.02. So remember, percent to a decimal, I'll just write that, percent to a decimal, you just divide by 100. And then I need to raise that to the power of n. N is the number of increases. So it's increasing each year for 20 years. So n would be 20. Now I just put that in my calculator. So if I put that in my calculator, I'm going to round to the nearest whole number. So it'd be about 520,082. So that's how many would be in the town after 20 years. Okay. Now I'm just going to show you an example of exponential decay. So let's look at this example here. It's the same example as on the last slide, the town with a population of 350,000, except this time the population is going down by 2% each year rather than up. So this is exponential decay. Decay means like it's eating away or going away. So here in the town, there are like people going away each year. So we saw for exponential growth that things increase at an increasing rate. The amount by which things go up increases each time. For exponential decay, we're talking about decreasing. Things decrease at a decreasing rate. So when we're talking about the population of a town, what we mean is the number of people that leave the town is less and less each year. So let's just have a look at how this might work if we do it the long way. So if I have a population of 350,000 and I decrease by 2%, note that decreasing a number by 2% is the same as finding 98% of the number. So at the end of the first year, I can find 98% of 350,000 and I get 343,000. So that's how many at the end of the first year. So that means the population's decreased by 7,000. So if I do this again at the end of the second year, I take my answer from the first year, 343,000, and I times that by 0.98. Again, I do that because decreasing by 2% is the same as finding 98% of the number, and I get 336,140. So I'll do this one more time. So at the end of the third year, I take my answer to the second year. Again, I find 98% of the number. And if I put that on my calculator, I get 329,417. That is to the closest whole number. So what you can see is in the first year, we lost 7,000 people from the town. The next year, we've lost 6,860, and then from the second to the third year, we've lost 6,723. So this is the amount that the population is decreasing by each year, and it is decreasing. Of course, we don't want to do this all the way up to 20 years. That would take too long. So what we're going to do is use a formula. It's very, very similar to the one we just used. So we had A equals A0, so the amount you start with times 1 plus the rate to the power of n. That is for exponential growth or increasing, but here we're decreasing. We only change one thing from the formula. That plus in the middle becomes a minus. And you can sort of see that from our example here, like 1 minus 2%, 2% as a decimal is 0.98, okay? Because decreasing something by 2% is the same as finding 98% of that number. So that is literally the only difference between the formula for growth and decay. The growth has a plus, decay has a minus. Let's use the formula on this question. So we started, A0 is how much we started with, and we times it by 1 minus the rate, which turns out to be 0.98, to the power of 20, because that's the number of decreases. And so the answer we get to the nearest whole number is 233,663. That is how many people will be in the town after the 20 years, okay? So make sure you understand the small difference between the formula for exponential growth and decay. Remember, exponential growth is when something is increasing at an increasing rate, and exponential decay when it's decreasing at a decreasing rate. Sorry for the long video. This has been the luckiest maths teacher in the world. Have a great day.